Alrighty, everyone. Welcome back to Fitting Potentials Part 2. So last time we talked a bit about when you might want to parameterize your own potentials and force fields, and also some of the things that you need to consider when choosing functional forms and methods. Now, this time I'll actually give you a specific example and show you how we apply genetic algorithms to solve the global optimization problem and fit interatomic potentials for a specific system. So if you recall from last time, we were interested in these modular and flexible molecules, the CDB shown on the screen here, where you can change the functional groups in order to tailor its properties and construct really cool coatings and different structures on the surface. Now, in order to do so, though, you almost need a new set of potentials for every type of molecule, right? And how do we create these potentials quickly and effectively when each one involves 40 or more parameters that need to be fit? So we can very quickly talk first about multivariable optimization as a problem, right? So the more complex your system is, the more parameters you need. So the more atom types, the more different elements you have, or if you need things like electronic structure information in your system, the more parameters you'll have to have. And this will manifest itself in terms of the functional form and the techniques that you'll need to use in order to parameterize your system. Now, there are a huge number of optimization techniques that you can actually use. So sometimes you can just try to use something like steepest descent or conjugate gradient, which are very common optimization techniques you can use during minimization of atomic structures, for example. And these are really good and let you find local minimum. But when you have so many variables, you end up with a really complex potential energy landscape, and you need something that searches instead for a global minimum. And there are many ways of doing this, including things like genetic algorithms, random search, or particle swarm. The one that I'll be talking about today is called genetic algorithm, and I think you will actually be getting additional lectures on other techniques during the rest of the course. So these types of techniques are used in many problems in physics, from things like structure search to energy minimization to transition state calculations. Now, genetic algorithms are a way of trying to use concepts that come from evolution in order to solve your multivariable optimization problem. Essentially, if you have a ton of different variables, you can treat each one as a gene. And one set of these parameters then defines a member. So this member has genes, and its genes are basically a unique set of variables. Now, many of these members make up some population, and we can create an initial population by just generating a lot of random members to create this generation zero. So you just take random numbers for all of your parameters. You do have to set a minimum and a maximum physical value for these things, right? So you know that some of these parameters cannot be zero because you shouldn't be dividing by zero in your potential form. You also know that some of them are not negative. For example, if you have a length dependent parameter, you can't have negative lengths. Now, once you have this random population, what you need to do is somehow compare how each of these members do in replicating the system you want. And this is called fitness, right? So how well or how fit this member of the population is for the task that you're looking at. Then you want to select the fittest members out of this population and mix them to create new generations. So you delete the ones that are not good at doing what you want, and you mix the ones that are good at doing what you want to create a new generation. Repeat this over and over and over again in your computer, of course, very quickly. And eventually you will produce population members that are very good at solving the problem that you want. So when you do this selection based on how well each member does at representing your system or solving your problem, you need a way of determining whether they're good at it, right? You do want to select two members and mix them together, but you want to select members that are good at their job. So how do you evaluate fitness? Well, you need to decide the fate of each parameter set or each population member. So you have to come up with a scheme to tell you how good it is at doing its job. In our example, what we did was we calculated the difference in forces on each atom within the calculation, and we summed up all of these differences over the entire fitting data set. And you do this for every single set of parameters or population members that you have. So this will give you the total fitness of the system if you define fitness as reproducing accurate forces on every single atom in the system. Now, sometimes this is not quite enough because you might also have additional experimental values or physical properties that you know are important. For example, if you know what the adsorption energy of the molecule on the surface is, you could add that in as another fitness criteria. So you could calculate the adsorption energy with each of these parameter sets and see how well they do at predicting that value and add that into the fitness as well. Now you do have to carefully balance all of these contributions so that not one of them can overshadow the rest. Now, once you are able to do that, you can simulate generations. So an example here is if you randomly generate 1,000 set of parameters, so a population size is 1,000, you can then calculate the forces on each atom for every frame of the DFT data and compute all of the differences between DFT forces and the classical forces predicted by your parameters and delete the worst members of the population. Then you generate new members. You replenish this population back up to 1,000 members by breeding the survivors, and you'll generate new populations or new generations, right? You can also introduce random mutations within the population. So you can say, okay, when I'm mixing members with high fitness, I can have a 1% chance of just generating a random gene instead of taking one of the parental ones. And that helps keep your gene pool a little bit more diverse. Now, I think a lot of you should be pretty familiar with the concept of convergence, right? So if you're running a density functional theory calculation or an energy minimization or something like this, often you determine when to stop the calculation by looking at convergence. And this is the difference between energies, for example, in between steps as you minimize a geometry. Now, in genetic algorithm schemes, convergence is very difficult to define and use in the same way. So if you look at the plot shown on the slide here, you can see all these jumps, right? So it's not a smooth curve as you go from left to right, as you increase the number of generations. And this is because you can have random mutations, or you can just have a lucky case of mixing that gives you vastly improved performance. You're not sampling the potential energy surface by traveling down the curvature, for example. So this becomes a really bad criteria to use when choosing when to stop your calculation. So instead, within genetic algorithm scheme, you can think of convergence almost using a completely different definition as when all the parameters have converged to the same value. So when all your parameters are the same, then it's obviously pointless to continue running the genetic algorithm because you're just breeding genetically identical members, right? You'll always get the same numbers out of it. And once you reach that point, you're relying only on the mutation rate to generate any new information. And you might as well be using a different method, something like a random structure search, for example. So convergence in this case is a good way of telling whether or not you're just wasting your time running the genetic algorithm. But it does not prove mathematically that you have found a global minimum. So once you've run this thing for a lot of generations, you want to examine the fitness and the force matching of the parameters that you've chosen in the end, right? So for example, in this case, we ran 1,000 generations and we picked a couple of the best members of the last generation. So you want to look at what the potential is good at and what it can and can't represent so that you know what it can predict when you use it for your other simulations. So in this case, for example, we can compare the difference in forces between the density functional theory and the classical potentials. So the density functional theory results here are the dotted line and the classical potentials are in red. So in this case, we've split the data that we're using to evaluate the potentials into 3 categories. Frame 0 to 80 is molecular dynamics data at 300 degrees Kelvin. So this is data that represents how the molecule might behave at room temperature. At 80 to 190 frames, this data represents molecular dynamics at 600 Kelvin. And from 191 to 210, this represents the interaction between the molecule and the surface as it's coming in from a large distance away, right? And if we just look at the difference between DFT and classical forces, you can notice that it's quite good between 0 and 80. The lines match up very well, so we have very low error. And it's also quite good between 190 and 210, right? So at room temperature, this set of potentials is pretty accurate. If you're looking at molecules dropping down from a large distance away, so deposition effects or even evaporation, it looks quite good too. However, in the area between 80 and 190 frames, you do see that there is a lot more difference between the classical and the DFT frames. And this indicates that if you're interested in really high temperature systems, that these potentials are not that good. So this can arise from any number of things, right? It could be that, you know, the system changes a little bit and you need a more adaptive force field potential form to account for it. Or it could just mean that we didn't fit it well enough to that environment and we need more fitting data in order to make it work. If we take an even closer look at the forces, we can divide them into X, Y, and Z contributions. So this is just the forces in the X direction in the system. You can see that the match is pretty decent, but there is a little bit of error. If you look at the forces in the Z direction in the system, you have the same story. So generally a pretty good match, but there are some small errors here. Now, X and Z in this case were directions parallel to the surface plane. If we look finally at the forces in the Y direction, which are forces perpendicular to the plane of the surface, we see that the match is very, very good. So we have great agreement in terms of the Y direction. And this actually makes a lot of sense because the molecule surface interactions that we fit generally interact along the y direction. And it's actually the molecule-molecule interactions or the interactions between atoms within the molecule that show up in X and Z. Now remember, we did not fit the molecular interactions as such because we are relying on the CHARMM potential. We only fit the molecule surface interactions. So these results actually show that our molecule surface interactions are very accurate in comparison to the quality of the force field that we started out with already. So once you have the best force field, you've got the best fitness, it appears to be converged, our error looks to be smaller than that of the original force field we used for the molecule itself. We notice that it reproduces adsorption energy well. We need to decide whether or not it's good enough to use in our studies, right? So you have to ask questions like, is it converged? This is really hard to tell because we discussed briefly that you can't define convergence in the same way as you could with density functional theory or with energy minimization. We need to also remember that it's only as good as what we put in, right? You can't generate classical potentials that are more accurate than your fitting data. And something else we have to remember is that solutions are not unique. So I'll come back to this again in the third video. But every time you run this genetic algorithm fit, or every time you train a neural network, you almost always get a slightly different answer because these solutions aren't unique. Your potential energy landscape is so complex, especially on the order of thousands of variables, tens of thousands of variables, that it's really difficult to mathematically prove that you've got the global minimum, right? You have a very good solution, but there might be other sets of parameters that give you a very similar answer as well. Now, the final thing that's also really important in the context of doing physics with these techniques is that you need to know when things have lost physical meaning. So a good example in this case are that the charges on atoms start to lose physical meaning when we apply these techniques and mix different sets of classical potentials. For example, the charges on potassium and chlorine in the classical potentials from Scott's UCL potentials library are assigned as positive and negative integer values. So they're plus and minus 1. So that's quite reasonable from a physics standpoint. But we know that in density functional theory, they will not be exactly 1. They'll be a little less, something like 0.8, 0.7. And we have then taken another force field where the CDB atoms are much smaller in magnitude in terms of charge. So on the CDB molecule in CHARMM, the charges are fit to density functional theory values. So they'll take some analysis, some Mulliken or beta analysis, calculate the charge that's attributed to each atom and assign them in that way. There are more complicated schemes, but that's the general idea. So when we look at the potentials we have fit, you can no longer assign a physical meaning to the Coulomb interactions between these atoms now, because one set uses integers while the other set uses density functional theory charges. And we have then fit everything so that the rest of the potential compensates for whatever error is present there. Right, so when you learn about things like Lennard-Jones potentials, for example, you learn that this term is the van der Waals, this term is the repulsive interaction, and then we add in Coulomb interactions between charged particles. But this does tend to fall apart if you start using potential forms as mathematical constructs rather than as physical ones. Okay, so just to finish this section off, I'll give you an example of what we were able to do with these potential sets afterwards. So essentially, you can then simulate a huge number of surfaces. You can compare your structures that are predicted theoretically directly with experimental structures. Then we can modify the molecules, predict more structures, and tell the experiments what they can do to change the film. So for example, the CDB molecule with a cyano group on the end creates these nice porous net-like structures. However, if we want to change the size of the pores, we can elongate the backbone by adding more rings to the backbone. So increasing the length of the molecule increases the size of the pores. We can also remove or greatly weaken the interaction between the functional groups and the surface in order to tune the structure to become line structures. So instead of a porous mesh, if we replace the cyano group, we can get line structures. And eventually, if you replace the cyano group with methyl groups and really weaken that molecule surface interaction so that the molecules interact better with each other, you start to form molecular crystals. So things like 10 plus nanometer high crystals rather than monolayer structures. So depending on what functional group you put on the molecule, you can qualitatively change the types of structures you build. And each of these structures represents something that might be useful for a different application. So if you were trying to protect your surface, you might want a really thick molecular crystal, like this CDB methyl gives. Or if you're trying to create a framework for catalysis or reactions, you might want a porous network, for example. Right, so that's the end of this video. The next video, I'll give you additional case studies, so other examples of what we can do with these techniques. And we'll talk about how you might be able to apply them in your work. So you can do anything from fitting models to experimental data to helping create new quantum mechanics, molecular mechanics, modeling schemes, to creating properties predictors with machine learning. All right, thanks for watching. I'll see you next time.